This one is a homework problem from our book. It uses continuity, and we're trying to calculate a limit. So let's see what we're told here. In fact, we're told something more than once, but this is what I'm going to focus on. What does this say about the function? It says that f is continuous at 7. So we see f is continuous at 7. It's exactly what those two say. Definition of continuity, that the limit equals the function value. And then, well, you see, this is what I was saying. They sort of tell us twice. Okay, f is continuous. They tell us again, but the limit on the inside exists. And whenever you have a continuous function and the limit on the inside exists, you can bring the limit inside. And so what that means in this situation is the limit as x approaches 5 of this composition is f of the limit as x approaches 5 of g of x. This was continuity that allowed us to do this. And this is f of, where we're told this limit, 7, and f of 7 is 5, okay? So this is our answer. Now, another example, and I wanted to do this in class, but we didn't get to it, is the limit as x approaches infinity of ln x plus 1 minus ln of x. This is a really great example. If you think about what's happening, natural log, let's graph it. It goes to the point 1, 0, and kind of looks like this. Okay. Go to this point. This is more or less the shape of y is natural log x. We see the limit as x goes to infinity of natural log of x, or natural log of x plus 1, is infinity. But this is not equal to 0, okay? Infinity minus infinity is nothing. You can't say anything from that. Infinity minus infinity doesn't make really sense, right? Because you don't know. You don't have any conclusion. Kind of like 0 over 0 or infinity over infinity. So we have to do something else, okay? And what I would do here is, first we can use a log property. And then we can use the fact that natural log is continuous. Oh, I need my limit. This is a limit as x approaches infinity of, well, there's a property of logs. If you have a difference of logs inside, it turns to a quotient. So this would be ln of x plus 1 over x. Okay. Now, what's inside this log? Well, I can simplify this further. This is 1 plus 1 over x. Okay. What's inside the log? As x grows without bound, this approaches 1, right? And so, natural log is continuous. I can bring the limit inside. This would just be, maybe I'll do it in 2 steps. Okay, this is ln of 1, which is 0. But be careful. It's not 0 because infinity minus infinity is 0. It doesn't work like that. It's 0 because of log properties and properties of continuous functions. Okay? I like this example. Now, the last one is another textbook exercise, and it's a word problem, and it really is about limits here. We charge, or the supplier charges 80 cents per CD if you purchase 500 or fewer. And then it charges 72 cents per CD if you purchase 501 to 1,000. And then it charges, okay, 65 cents per CD if you purchase more than 1,000. So what do we want? We want an equation for price and then cost, and then we will calculate some limits. This is a fun function. Price, well, this is piecewise defined. We see it here, it's 0.80 if you are between 0 and 500. I guess I could put it open at 0 because you wouldn't pay 80 cents for 0, or maybe you would. I'll leave it like this, it's fine. And then if you are bigger than 500 and less than or equal to 1,000, the price is 0.72, so 0.72. And finally, if X is bigger than 1,000, the price is 0.65. Okay, this is price. This is part A. Now, what we want is cost, and then we can calculate a limit from the left and a limit from the right, 1,000. Okay, well, let's think about cost. All we do to get the cost, if each one costs, say, 80 cents, and we buy X of them, the total cost is 0.8 times X. And similarly, if we were in this part, if each one costs 72 cents and we buy X of them, we pay 0.72 times X. And so I think I can just copy and paste. Okay, this is the beauty of the GoodNotes app, and just change, because all I need to do to get this formula is multiply by X, and we have the total cost. Okay, this is the cost function. Now, to get the limit from the left and the limit from the right, let's see. I will do it from this algebraically, but then we can look at a graph of this function. On the left of the cost, well, the left, it uses values less than 1,000, and this would be this formula. So we just evaluate this at 1,000. That would move the decimal place 1, 2, 3. We would get 720. And if we want the limit as X approaches 1,000 on the right of the cost, well, we use X values bigger than 1,000, and that's this formula. So we evaluate this at 1,000, it moves the decimal over 3, and we get 650. Okay, so this is the limit from the left and the limit from the right, where I calculated it from this function. And then, okay, this is our cost function. You see the limit coming in from the left is here. It's, well, we don't see it exactly, but we calculated 720, and that certainly looks reasonable based on tick marks. And then the limit coming from the right is, we calculated, was 650, and that also, that we can pretty much see. Here's 700, and here would be 650. This is the limit from the right. And this function, just to go back to continuity, this function is not continuous at 1,000, is not continuous at 500, right? That's where we have these jumps. Okay, that's all I have to say. Thank you.